all recording. We'll double check on the capturing. So it is capturing just fine using the microphone. And we'll wait for the door. It's not too bad. We can bump it up a little bit. There we go. All right, so I worked on the design a little bit more. It's not done yet, okay? But I did add, one important component into the design, which is the ALU, the logic, arithmetic logic unit, and also the program counter, the PC program counter is also added to the design. So the first thing we'll do is to kind of take an overview of how it is different from before, from last time. There are some minor optimizations too, but they're not, as it's not a big deal. Okay, I optimized one of the buffer out of this part here. So before there's a buffer and it's really not needed, so I took it out. I added an instruction register. We'll talk about the instruction register and how it interacts with the registers as well as the ALU. So that's going to be one big part of today's lecture. I also expanded the program counter circuit. So the program counter circuit is a little bit different from last time. Instead of just a register, it is now kind of like a sub-circuitry. And this is the program counter part. I'll explain that part also. Yeah, so this is a little bit new. We will, I will go ahead and label the pins, accordingly when we get to those in specific parts. If there are any questions, you might want to ask the questions, right now, because we are at the beginning of the class. We can certainly go over some of the topics that we have talked about so far before we get into the newer stuff. Are there any questions regarding the design from last time? No questions? So this is all going okay with you guys? Okay. All right. So what we'll do is I'm going to expand this part first. Okay. The registers have always been here, but I have made connections that are slightly different from last time. So we'll go focus on one specific part of the design at a time today, and go over that part, and then we'll go ahead and actually do a simulation of, okay, let's make it work. Okay, let's do certain things like add two numbers or something like that. So we'll go ahead and do all that stuff today. And I will label these pins also. So this is the registers. Okay, this one is just the it's a sub-circuit that contains 4 individual registers. It has the ability to update one register at a time. It also has the ability to output 2 registers at a time. Okay, so it's 1 in, 2 out, and select from a bank of up to 4 registers. Okay. The reason why we have 2 outputs instead of only 1 output is because of the ALU. So let's go ahead and label this thing first. I'm gonna put a label, just plain text, put a label here, just so that it's easy for us to remember what this is. So these are basically just a bank of registers with the appropriate control circuits. Oops. No. I just want to move the label. And it's not letting me. That's okay. I think you can still see it. It's just not as clear. If I would like to put it into the center part of the box here. Okay, so there are 2 control circuits here. There are several lines. So we'll go ahead and explain each line and how it's connected. This one is register in select. Right now it's connected to a pin. It basically specifies when I'm updating a register, which one am I updating? I can update one of the 4 registers if I'm updating a particular register. So right now it is selecting 0, 0. And what I'll do is I'm taking this away. So I'm going to take these 2 pins away and make a connection to here. So the register select 0 is going to be the same thing as register input select. So they're always kind of tied. It just makes the design a little bit easier later on. And then the other pin here, okay, these 2 pins control register write enable, and also the clock signal for updating the registers. In other words, if this one is a 0, you can clock all day long and nothing happens with the registers. Nothing gets updated. In order to update a particular register, there are four things that you need to do. One is to specify what is the new content of the register. Two is to specify which register needs to be updated. Three is to enable the register write enable pin, turn it to a 1. And then the fourth thing, which is the last one, is to have the clock signal to have a transition. And I think from last time, we observed that the transition has to go from low to high. So that transition basically tells the registers inside that box here and say, okay, it's time to update. Everything is now set up, okay? The proper data is on the data line, it's input. The proper register is selected, 1 out of the 4. Write enable is turned on, which means, okay, pay attention. And then the clock signal eventually just says, okay, now sample the data lines and use whatever you sample from the data line to update the internal state of a register. So those are the 4 steps in general, of what you need to do to update a register. These pins are still outside, I don't have anything else to hook it up to. So for simulation purposes, they are all tied into the output here so that we can toggle these pins explicitly, manually when we have the simulation tool or change value within circuit tool selected. So we're moving on to the other pins. Okay, let's look at this pin here. Okay, this is input register selection, which means which one am I updating? It is tied into this node here, to this pin, which is register 0 select. This is the output register select 0. And this one is register enable 1, which means if this is a 1, then output register 0 will be turned on. The other one is output enable 0, which means if this one is on, then the output register 0 port of all of these registers will be active. And then we have this line here. This is the reset line, which is a global line that has to go everywhere within the processor, so that when reset is asserted, all of these circuitries, all of these registers will basically go all the way back to 0, a known state, as the initial state. Now, what is kind of interesting, what is new this time, is what I call an instruction register. An instruction register in this case is an 8-bit register, but the output of this particular register is broken up into at least 3 parts. Okay, so right now we have 3 parts. Bit 0 to bit 1. Okay, this output here has 8-bit. Okay, this is an 8-bit wide output. It goes into the splicer here. The splicer separates the 8 bits into 3 basically logical components. The first logical component is bit 0 and bit 1, and that goes to both this part here and also this part here. In other words, it is used to specify if we are updating a register, it specifies which register am I updating. If we are outputting, it is specifying which one of the 4 registers, A, B, C, or D, is output 0 from the register bank. Are we kind of doing okay so far with that? Okay. And then the other 2 bits, bit 2 to bit 3, is going into this particular port here, and that's selecting which register, if any, do we want to select as output register 1, okay, or output 1 from the register banks. And once again, we can select register A, B, C, or D as output 1 from the register bank. Are we doing okay so far? Okay. So if you want to, you can select the same register, let's say register B, to be both output 0 and output 1 from the register bank, so you can add a number to itself, and then in a later step, you can store it back into itself. All right. So this is a new thing. For bit 4 to 7, there are 4 bits there. They are unused at this point. Okay. At some point, we're going to have to use those. Okay. There are 4 bits, which means we have up to 16 combinations, and those 16 combinations will be used to implement, about 16 instructions that we'll be writing later on. Okay. But right now, we don't have the microcode architecture done yet. So I'm leaving those 4 pins not connected to anything, but they will be connected to basically the heart of a processor. Okay, the glue that glues all the components together. When you see all these pins floating around, with the exception of the reset pin, they really should not be floating around. They should all be connected somehow internally within the processor. The only reason why these pins are quote unquote floating around is because we don't have the glue to glue everything. So I will have to manually set stuff to say, okay, select this register, write enable here, clock it, and do all the stuff, manually. But eventually we'll have everything automated using a state machine and a microcode architecture. All right, so the instruction register, just like any other register, has a few other pins. It has a D port, which is this is the only way to specify the new content for the instruction register, and it comes in directly from the data bus. In other words, it connects straight to the data bus of memory. So whoever is driving the memory bus or the data bus can potentially be used to update the register, the instruction register. This is the enable pin of the instruction register, or the write enable to be more exact. So we'll go ahead and label this and say this is our instruction register write enable. I know the names are getting pretty long, but they kind of have to be long, like at least like this, to describe what the pin does. Okay, because otherwise, it will be kind of difficult to find out. Okay, which pin should I toggle next? Because I cannot really see, what the pins are actually doing. The other pin with a little notch here, if you do a magnification, let's turn up the magnification. There's a little triangle here. Okay, there's a little triangle to the north of the light green circle. That is a symbol of a clock input signal. Okay, when you read the schematic diagram of a chip, that usually means okay, it's a clock signal, which also means the transition on this line is the part that is important. Okay, the transition causes something to happen. And this is a rising edge trigger. You can actually select whether you want it to be rising edge or falling edge, or the enable is actually high level or low level. At a hardware level, rising edge or falling edge is much more common than just saying, okay, if it's a high, you want to update the content of this particular register. So I'm going to label this label here. I'm going to label this pin here because it connects to the clock signal, and we'll call that the instruction register write clock. So we need a transition on this line in order to specify new content in the instruction register. And at this point, we will change the location to east, just so that we can see it more clearly. All right. So are there any questions about the instruction register? The instruction register is basically the one register that holds the content of a particular opcode temporarily. And out of the instruction, which is basically just a bit pattern, it breaks it up into small components. Like in this case, for this particular architecture, an instruction can specify up to 2 different registers as output. It can specify 1 register as an input, and so on. Okay, so it specifies how to perform a particular operation. Bit 4 to 7, eventually it will be used to program to specify the microcode, which will specify what type of operation we want. Do we want to subtract? Do we want a compare? Do we want to multiply? Do we want a division? Stuff like that. So bit 4 to 7 will be used for that purpose. But at this point, we don't have the glue to do that just yet. Okay, it's because we're trying to do it kind of one little step at a time. Moving down a little bit, the indirect register is pretty much the same thing as the other day. It really is just one way to specify, going through the mux here, to specify the content on the address line of the memory chip. So you can see the address port here is connected to the output of this multiplexer, and then the input of the multiplexer has 2 potential sources. One source is coming from the indirect register, and the other source is coming from the program counter. The program counter is all the way over here. So this is the output of the program counter. It goes to the other input of the multiplexer. So we have two ways to specify the content on the address bus. And once again, the content of the address bus, the bit pattern on the address bus specifies which location in memory do we want to do something with. Do we want to read or do we want to write? That's controlled by another pin, but the address bus specifies which location are we dealing with. Are we doing okay so far with all of this stuff? Okay, so some of this stuff is new, but for the most part, they're not. And this, okay, this is a pin that connects to the clock line of the indirect register. So we'll give it a label and point it to the west, and just say this is our indirect register write clock. Okay, just so that it's clear, what the pin does. And this one is the enable pin. So we'll go ahead and label it as indirect register write enable. At some point, we will be able to just know what each pin does, from where it's coming from. But at this point, we'll label all these pins, just so that it is, more explicit. Now, the program counter last time was really just the program counter itself without all this extra stuff. So now it has some extra stuff, connected to the program counter. What it is for? Well, let's go ahead and take a look at some of these locations, or some of these extra circuit connected to the program counter. The Q port of the program counter, this part here, this is always, the output of a register. In other words, with this particular type of registers, you cannot say, oh, register, stop outputting, do not drive the output. Okay, it's always driving the output. Whatever content you have, or whatever memory, or whatever content the register is currently storing, which is 00 in hexadecimal in this case, is always driving the output. So the Q port is always the output, is always driving. So in this case, it's driving two things potentially. One is it's driving the multiplexer here. We talked about it already. The other end of the multiplexer connects to the address bus. So potentially the program counter can drive the address bus to specify which location we want to access next. But it can also be it also drives concurrently the adder here. Now this adder is kind of funky because we are not adding anything really specifically. So you can see that one input comes from the program counter. Let me point out which port we're talking about here. So this port of the adder is one of the numbers to be added, which is coming from the program counter itself. The other port is connected to the constant of 00. So we are not really adding any arbitrary number to the program counter. We are just adding 0 to the program counter. So it's useless, right? Well, it's not exactly useless, because the carry in can either be a 0 or 1 because it's hooking up to a pin, and I label the pin PCINC, which stands for program counter increment. Do we want to increment the program counter or not? Okay, so we have a choice of whether to do it or not. The output of the adder, which is this port here, okay, if you read the comment, it is the output, the sum of the outputs. So we are either adding 0 or we're adding 1 to the current value of the counter, or of the program counter, and it goes around and all the way back, not directly to the input of the program counter, but it goes through a mux, okay, a multiplexer. This multiplexer, just like any other multiplexer, can choose one of the two potential inputs and connect one of the two inputs to the output. So one input comes from the adder itself, which is this path here. The other path, if you follow the line here, the other potential input is coming from the registers. So it goes all the way here and go to this particular pin, which is the output port 0 of the register bank. In other words, out of the 4 registers, A, B, C, or D, okay, there is a way for me to use one of the registers to update the program counter. Okay? Now, that is an interesting thing to do. Program counter, as the name implies, is basically a bookmark that tells us, okay, where in the program am I executing at this point? Okay, if you consider an entire program as an operation manual, a book, a thick book, that tells you what to do, this is a bookmark so that you don't lose track of, which page you're on when you're following instruction that is written in the manual. Okay, the program counter, serves that purpose. So the ability to use a register, A, B, C, or D, to update the program counter allows us to jump from one location to another location. Okay? So it is going to be used for the purpose of what we call the go-to statement in C and C++ that you were not supposed to use in your previous classes. But in assembly language programming, that's the only way for you to alter the path of execution, other than just the next instruction. The next instruction, you only have, well, okay, I wouldn't say that that's the only one, but that's the basis of all the control structure written in assembly language. Okay, so that's how that is connected. The program counter can either be updated based on one added to its old value, or it can be updated by one of the registers using this particular marks here. So it's a good time to label these particular pins, just so that we know what each pin does. So we'll go ahead and kind of move these things around a little bit, just so that they're easier to read. This particular pin here, make the label face east, and this is our PC program counter right clock. Okay, so whenever there's a transition here, you're saying, okay, go ahead and update yourself. This one here, also make it face east, is our program counter right enable. In other words, if this line is low, then you can clock it all day long and nothing happens. This one here is a mux. It allows us to select, do we want to update the PC from a register, or do we want to just update it after an increment? Okay, do we just want to add one to it? So that line is going to be, we'll label it, we'll also make it face east, and we'll label this one as PC source. Now this is something that I personally use. Whatever is following means if it is a 1, that is selected. So if this line is a 1, it's going to select the increment. So I'm going to say increment is the first one, and then I use a slash to imply, okay, if it is not a 1, that is the source. So if it is not a 1, it is coming from a register. So the source comes from a particular register in that case. So it's kind of like a long name, but I like the name or the pin label to kind of reflect what it does. Okay, so let's go ahead and test this out, okay? Because the one thing that I want to test at least is to see whether it can increment itself or not. So let's go ahead and see what we need to do in order to increment the program counter itself without doing anything else. Okay, all we want to do is to update the program counter so it goes from 0 to 1, 1 to 2, and so on. First thing first, we have to change the program counter increment pin to a 1 to basically say, yes, we want to increment. We don't want it to stay at the same place. So once it is turned into a 1, the output from the program counter register itself through the Q port is going into one of the input of the adder. The other input is tied to 0, which means we are not going to add any arbitrary number. But since the carry in is also added to the adder, so we are just adding 1 in this case. So coming out of this port here, coming out of the output of the adder, is going to be the sum of 0 and 1 in this case. It's going into the mux here, but the mux is selecting port 0 at this point. We have to change it to a 1, so it's selecting the incremented result of the program counter itself. Nothing is happening now because I have both of these pins tied low at this point. So the first thing we have to do is to turn this pin to a 1 to basically say, hey, program counter register, pay attention now. Okay, sample the input from the D port and also pay attention to the clock line to look for a transition. But before the transition happens, nothing is going to do. The register doesn't do it. The register doesn't do a single thing. So now I have everything all set up. I will do a 0 to 1 transition on this register, and it updates to a 1. Okay. So I have done what is needed in order to increment the program counter by 1. And once it's done, the as the name implies, the clock line is only intended to go high and then goes back to low again, because we are only looking for that one transition. So with any clock line, after the transition that we are looking for, you almost always want to clock it back down, to a 0 after the transition that you need. We can also, disable program counter write enable, because we don't always want to, update the program counter. It's always safe to turn it off first. This one, we don't have to turn it off, unless we have a good reason to, because it doesn't really affect the program counter unless these pins are also selected. So we can leave this one the way it is, as it is now. So the output of the program counter should be 0, 1 at this point. Are we still doing okay so far at this point to understand this kind of sub-circuit of how the program counter can update itself, at least do the increment? Okay, yep.
So if the program counter write enable, the one that you have highlighted, if that's set to 1, so the register bank above could still access the PC or the program counter? Is that what you're saying?
Okay, you mean the program source increment? Oh, the one that I have selected.
PC,
write enable?
WREN. If that's selected to 1,
Yeah.
the register bank above it is still able to access the program counter?
No, the registers cannot access this particular register. The program counter itself, the output of the program counter, only goes to the address bus.
Okay, I was talking about the registers above that connect to the MUX.
Okay, so here's the MUX. The other input goes, to this node, and that node goes all the way to, the output 0 of the registers. So right now, because of the MUX, we are only selecting the bottom part of it. We're only selecting the other port. So if I turn it off, then it'll be selecting from the output of the registers, right? But here it is already, it's not enabled yet. If you look at this line here, register output enable 1 and register output enable 0 are both 0. So that means this is not driven yet. It's not specifying any particular content into the input part of the MUX. Okay. Any other questions? Yep.
If you were to enable writing from where you're selecting from registers, would it just give you random data, or would it just give you nothing, zeros?
Physically, it would just be whatever voltage the register will sample at that time. If nobody is driving a particular line and is floating, then it depends on a lot of other factors, whether the line is going to be high or low. Typically speaking, if it is a very high-speed operation, the charge or the capacitive element of a particular line will retain the voltage for a particular amount of time. So you might see the quote-unquote ghost signal from the previous state, but it's not reliable because it can go either way. It's just a matter of time before the capacitive before the charge due to the capacitive nature of a trace goes away. Yep. And there are voltages. This is also I know it's a little bit out of context because we are only focusing on the logical aspect of the processor, but when you think about it, the hardware aspect is also important. The way that it works is, at a very, when we look at time, when we really stretch out time, and this is really looking at a very small amount of time, there's no way you can actually raise a voltage from 0 to whatever high voltage that the processor considers as high in an instant. There's no such thing as a square waveform. Okay, it's always curved. The only question is how curved is it? Is this time frame 1 nanosecond? Is it 1 microsecond? Or is it 0.1 nanosecond? That's the only question. Okay. The way the registers the way the transistors work inside the processor is it will register anything. Oops, this is coming out. The way it works is it has a threshold, and say everything below this line is registered as a 0. and everything above a particular line is registered as a 1. But what about all that stuff in between? It's not specified. Okay, so if you have, during this time here, a particular bit can be considered a 1 or a 0. We don't know. Okay, so that's why you have to wait until the voltage has settled down to either to this region or this region before you say, okay, now that particular line has a definite 0 or 1. Sample it and take that as an input. But when it's transitioning, when it's going through this stage here, the other side can register the voltage as a 0. It can also register the voltage as a 1, or it can fluctuate, just go like this during that time. So that's why you don't want to latch, you don't want to tell the other part and say, okay, take that as an input when it is still in transition, because it just doesn't know which way to interpret this particular voltage. Okay, there are special circuitry also that will give you the ability of saying, do not change the state unless it is more than a certain threshold, instead of when it's between the threshold, oh, you can do whatever interpretation. Either way is fine. Okay, but in this class we are not going to talk about that type of circuitry. In embedded systems like the AVR, anything that you use for actual control, it is important to build in that ability into the input pins so that the software doesn't get confused when the voltage is quote unquote in between the thresholds. Right. So now the design is not all done yet. Okay, the program counter eventually will also need to have a path to go to the input of the registers. In other words, we will need the ability to copy the program counter into the registers. Okay, but we are not doing that just yet. Okay, we're not doing it just yet. All right. So now that we have all this fun stuff here, let's go ahead and see if we can manually specify all of these things so that we can grab the content of 2 memory locations, put it into two different registers, and add the 2 registers and put the result back into one of the registers. Okay, so that's all we're going to do today. Okay, I think we have probably just enough time to do all that. Okay, it's a very simple instruction. Okay, what we are proposing to do, will be done usually in 3 different instructions. The first instruction is to go to a certain memory location, get the content at a certain location, put it into one register, let's say register A. Go to another location and put that content at that location into register B, and then the third instruction will add the 2 registers, and then the output will go back to whatever the first register is. Okay. So that's all we're going to do today. And all right, so first thing first, okay, we'll go to memory here, and since we do not have the ability to update it from within the system, we're going to have to update it by clicking it and specify new content. This is location 09, so we'll change the content of location 09 to, let's say, A3. A3 is specifying the bit pattern of 10100011. And we'll just pick another random location. Well, not exactly random, I just pick it so that it's, I don't have to scroll, it's already on screen. So we'll change this one to 03, which is 00000011. Okay, I want to read this memory content into register A, and I want to read this memory content into register B. Okay, so now we have to specify, okay, but how do we mess around with the address bus in order to specify, the location of memory to read from? That is not the job of the program counter, because I'm reading data, I'm not reading instruction, so that's not really coming from the program counter itself. It will come from the indirect register in this case. So for the indirect register, we have to specify the addresses. Let's do with 03 first. Okay, so I specify 03. I'm doctoring this in. Okay, I'm not using the processor autonomously to set the indirect register, because we are lacking the glue that glues everything together. Okay, so I'm just going to doctor and say, okay, let's go ahead and use 03 as the content of the indirect register. And then the second thing we have to do now is to specify, use the indirect register to become the output of the multiplexer, but that's right already. Okay, the address selection is already a 0, which means it is coming in from the indirect register. So that also means the output of the mux here is already using 03 as the content, so it goes into the address bus. Nothing is happening with the memory chip at this point because the selection pin is a 0. So the first thing we have to do is to specify what type of operation first. We are reading from memory, so the read line here, this line has to be a 1 in order for the memory chip to drive the output. We also want to click the select pin here, just so that the memory chip knows, oh, okay, I should pay attention now. Okay, are we still doing okay so far? The memory chip stuff, we talked about like a few times already, so I'm hoping that by this time you have some vague, idea of how it works. The clock line is not needed here. The clock line is only needed when we are writing, when we are updating memory. But when we are reading from memory, the clock line is not useful. Okay, it's just drive the output as soon as we read write is asserted, and also selection is asserted. So right now, 03 is now presented onto the data bus. So if you follow the data bus, it goes to, well, it doesn't go in this way, right? Because there's a buffer, it only goes in one direction. So instead of going into here, it is actually going up here and going through this line here and into this mux here. This particular mux allows us to select one out of two inputs. One input is coming from the output of our ALU, and the other one is coming in from the data bus itself. We want to select the data bus, which means we want to select input 0, and currently it is already selecting input 0, which is what we want. I should probably label these two, so go ahead and just label this one, and it is a data bus selection into the registers. So we'll label this on the east side, and we'll just say register input source. Okay, then the source, if it's a 1, it's coming from the ALU. If it's not a 1, it's coming from the data bus. Okay, so a 0 means it's coming from the data bus. So now this line here should have the content of 03 because we are reading from memory at this point, and it goes into this port. The port here of all the registers is the input to all the registers. Okay, so now we have to specify. Okay, let's go ahead and use that to update register A. Register A is 00 in the registers. There are several things we have to do again. We have to select a register 00. Now, we don't have a special pin to update that anymore. So it is now coming from the instruction register. The instruction register is broken up into 3 parts, as we talked about earlier. To specify the input, is coming. We are updating register A, means bit 0 and bit 1 have to specify 0, 0, which it is already, okay? Because the content of 0, 0 in the instruction register means we have 8 bits of 0 in the instruction register. So we are already driving. Okay, let me just kind of explain that part here. So out of these pins here, there are 8 pins coming out of this. They're all zeros, which means bit 0 and bit 1 are also all zeros, and that is used to specify which register am I updating. Okay, so we are now ready to update register 0. When we are ready to update register 0, we say let's go ahead and update. Okay, so we say write enable, and then make the clock line toggle once. Okay, make it go high, make it go low, and now register A should be updated internal to the register bank. Are we kind of do okay so far? So in the next instruction, we are ready to read from the other location. Okay, the other location is location 09. So to do that, we have to, okay, let's turn this off first. The other thing, so we have to update the indirect register to reflect the location that we are updating. So this time we are, not the indirect register, not the instruction register. So the indirect register now has to be updated to 09, which is the location that we are reading from. but we are not putting it into register A anymore. We want to put this into register B. Register B is selected by the bits 0, 1, and that 0, 1 has to come from bit 0 and bit 1 of the instruction register, which means the instruction register can no longer be 0, 0, because otherwise I'll still be specifying update register A. So we have to change this one to 0, 1. Well, one of the numbers that will work is 0, 1, because in 0, 1 hexadecimal, it is 0, 0, 0, 0, 0, 0, 0, 1 in binary. All I really care is the least significant 2 bits to be 0, 1, which works in this case. Okay? So now we're selecting register 0, 1. The order is not really important. Okay? This part versus how we deal with memory first is not really important. Okay, so memory is selected by the indirect register, and we have to make sure this mux here is selecting input 0 from the indirect register, and it is. So going to memory, we now have location 9 selected. Okay, because the memory chip is still selected here. The clock line is not useful because we are not updating memory at this point. The read-write line is a 1, which means we are selecting the read, and so it's driving the output. So the D port of the memory chip is now driving this line here, all the way to the input mux. Well, no. To the input mux here. The mux has bit 0, has a 0 selecting port 0, which is what we want, and it's going into the register bank, the register input of the register bank. So now we are ready to update register B. Okay, because the register B is now selected by the instruction register, or bit 0 to bit 1 of the instruction register is now selecting register B, and the data is now driven already. So it's time to turn on the write enable pin to basically say, okay, we're almost ready. Go ahead and update the register. Everything is now ready. We clock it, toggle the clock, turn off the write line, and now register B of the register bank should be updated to C3 as its content. So we have executed executed one instruction to read from location 03. We executed another instruction to read from location 09. So register A now has the content of location 03, and register B now has the content of location 09, which has the content of C3. Are we still doing okay so far at this point? So the next one is called the add instruction. Okay, the add instruction allows you to specify, okay, what numbers are we adding? Okay, the way this is set up is we can only use the registers to select, okay, let's go ahead and add these to the content of these registers. Okay, so this time we can work kind of backward. In other words, we look at the ALU and say, how do we get register A to be one of its input, and use register B as the other input? So you look at this port here. Let me switch back to the selection tool. So you look at this port here. It's data in 1. This is data in 0. So we now can use one register to specify D in 0, and the other register to specify D in 1. D in 0, if you follow this trace here, comes from here, which is our register port, output port 0 of the register bank. The other one, which is D in 1, comes from this port here, which is our output port 1 from the register bank. So what we need to do now is to change the instruction register so that bit 0 and bit 1 would specify register A, which means it's a 0, 0. Bit 2 to bit 3 will have to specify 0, 1 to mean we are dealing with register B. Are we still doing okay so far? Okay. Okay, so the binary number that we really need for the least significant 4 bits would be 0, 1, 0, 0. Okay, 0, 1 for bit 2 and 3, and 0, 0 for bit 0 and bit 1. Okay, let me just write it out here. We need 0, 0 to specify register A. We need 0, 1 to specify register B. And we want this to be the register that will also store the result. And that's why it is the least significant 2 bits. This one is just specifying the other number that we want to add to the first number. So that's why this is bit 2 and bit 3. This is the bit position, bit 0, bit 1, bit 2, and bit 3. Okay? And that forms the least significant 4 bits of the instruction register. And, and since the instruction register is specified in hexadecimal, this is just 4. The most significant 4 bits of the instruction register is not really used, so we can set it to anything we want to. We just have to make sure that the least significant 4 bits will specify 0, 1, 0, 0 as a binary number. Are there any questions about this part? Questions? Okay. So now that we have this done, this particular instruction, adding from 2 register and storing the result back into a register, does not involve memory at all. So the instruction register, hey, we don't need to use it. We're not going to touch it. In fact, we're not going to touch memory at all. We'll leave the other side completely untouched because everything that we are doing in this case is only involving the register banks and also the ALU, the arithmetic and logic unit. All right, so with these pins already set up, the output of the register bank should now have this pin here, or this port here should now be specified, should have the content of register B. This should have the content of register A, and both of those will be now driving the inputs of the ALU. We also need to specify what operation we are dealing with in this case. So that means these 3 bits here that we use to select which operation will also be, we need to specify that. So just going back to the ALU exploded view, we are now trying to specify operation select here, which is basically selecting which input from the mux we're selecting from. Addition is going into input port 0, which means we should specify operation 0, 0, 0 in this case for addition. And it is already 0, 0, 0. So right now at this point, the output, once it is enabled, is going to specify the sum of the 2 content that we have programmed into memory. Are we doing okay at this point? Okay. The output is connected to this pin. So this pin here, or this port, this is the output port of the ALU. It goes into this mux here, which also means at this point we have to select 1 with this mux, so that we are now using the output of the ALU to feed into the register bank. Into the register bank here, this is the input port. It should now be connected to the output of the ALU. And now it's time to specify, oh, okay, let's go ahead and update the register. Are we still doing okay so far? Okay. So to update the register, which is the same register as the first one to supply a number to add, which is register A in this case. So now we can go ahead and update it by saying register write enable. Okay, let's go ahead and get ready for the write operation. Do a low to high transition. Okay, so we are only updating during the transition. After the transition to high, it stays there. Just go, okay, we're done. Okay, which is important. So we go 0 to 1 to update register A to be the sum of the 2 numbers. Turn it back into 0. Turn off the write enable, and now register A of the registers should have a new content. Should have the content of the sum of the 2 numbers that we are dealing with. But I can claim that all day long, and you wouldn't know the difference, right? So how can we tell that, oh, register A is actually the sum of the 2 numbers that we were adding? We will need a 4th instruction. Okay, first instruction is to read from the first location into register A. Second instruction is to read from the second location into register B. Third instruction, add the 2 numbers of these 2 registers, store the result back into register A. And then the 4th instruction, just so that we can see whether it works or not, store the sum into a 3rd memory location. Is that okay so far? So let's go ahead and pick a location in memory to store the sum. It doesn't really matter which one we are using. Just pick one, right? So we go to the indirect register, which is basically a register to specify, in addition to the program counter, which address am I dealing with, with this particular instruction. So now we can say, let's go to location, I don't know, how about 1A, okay? This is a hexadecimal number, so 1A actually translates to location 26 in decimal. Because the A is the least significant nibble, it specifies 10, okay? And then the 1 is the most significant nibble, and that is 1 times 16. So 1 times 16 is 16, 16 plus 10 is 26. So in decimal, this is location 26, but in hexadecimal, it is location 1A. So we are now saying, okay, let's go ahead and update that location with the sum of the addition. So this is coming into port 0. We use 0 to specify the address port. That's all good. We go to the memory chip here, and then we say, oh, okay, you are selected, but you know what? I don't want you to be driving the data bus. Instead, I want you to be receiving from the data bus. Okay. So, but at this point, it's not paying attention to the data bus just yet. I have to do a few other things first. So at this point, I have to specify from the registers the output. Oh, right there. Okay, so as far as the register is concerned, this pin is now driving the data bus, but I have to make it. I have to enable it first. So now I have to enable. Oh, you know what? I forgot something. It may not be adding those two numbers because I forgot to enable the output when I perform the add instruction. So it may not have worked in this case. We'll find out. I should have labeled these things too. So let's see. This one connects to register outputs 1 enable. So we'll have to label it. I forgot it. I forgot about this. Register output port 0. Is it 1? Yep. Enable, and then the other one be the other one. Register output 0. Enable. So we might not have, actually performed the addition because I did not specify these two, which means, the ALU did its job, but there's no data to process when we perform that step. So we'll have to see whether that works or not. Okay, but we'll enable this one so that the registers will drive the data bus, and then go back to memory here and say, okay, it's time to update, do a low to high transition. It didn't really get the job done. I forgot about that step. Okay, so let's go back and redo that step. Redo the adding step. Okay. So getting back to the adding step, we'll have to specify the add operation here. Turn both of these ports on, okay, to specify both inputs into the ALU, and change the instruction too, because the instruction register is now a 1A, excuse me, is a 04. We want to specify, 04 would work. Okay. So at this point, the output of the ALU, which is this line here, would be the sum, and we're going to update register 00. Register A will turn on the write enable, clock it, and turn the write enable, turn it off again. So at this point, it should have the sum stored into the register. So the next instruction is to store into memory location. We can turn off register output port 1 because it's not really used for anything at this point. So we turn it off. The other one still needs to be a 0. And we go to memory here and we do another clock here, and it's updated to A6, which is the correct result. So I missed turning on the output of the register bank before we take the output of the ALU and store it back into the register. I missed that one step earlier. Okay. So how do you like being the processor? There's a lot of details, right? Turn this on, turn it off, clock here. Okay, now turn that on, turn it off, clock here. Okay, but that's the way it works, okay? So what I have been doing for the past half hour or so, 45 minutes, is acting as the microcode controller, the glue that basically holds everything together inside the processor. Okay, by asserting this line here first, clock it, and then assert the other line, clock it, and then wait until the output of this port is stable, and then clock the other one. That's the job of the microcode controller. Okay, if you think about what I did, okay, I haven't done it yet, but if you use a spreadsheet, okay, the easiest way to do it is to use a spreadsheet or any type of table, and you document the steps that I have done, and say, okay, first step, okay, turn this pin on. Step 2, turn this pin on and then turn it off. Step 3, turn that pin on. Step 4, turn this pin on. Step 5, turn that pin off, and so on. If you make a table out of that thing, you will see, in terms of the columns, you will have, like 0, 0, 1, 1, and so on and so forth. And what you want to do is to look at that as a, how do you call those pianos that can play music score by themselves?
Layer pianos.
Layer pianos, and they have special scores that they can read. Basically, they consist of holes to represent, okay, this is the note that you want to play at a particular time, and there's a big roller to keep rolling that thing, and that's what we're doing. Okay, we're basically just making that roller thing, okay, by doing everything by hand. If I record everything that I did, using a spreadsheet, that's basically the microcode that I need to specify for the load instruction. The load instruction is typically the name of an instruction to copy content from memory into a register. Okay, that's usually called a load register. So we had 2 load registers to load into 2 different registers. The third instruction is the add instruction. In this really simple architecture, I only have the pathways to add registers. I only have the option to specify registers as input to the ALU. Okay, I don't have any other ways to do anything. And then the third instruction, the fourth instruction is what we call a store instruction. A store instruction is seen from the perspective of the processor. It's copying the content of a register back into memory. So those are the 4 instructions that I executed. I kind of messed up the add instruction, so I had to redo it. But other than that, those are the instructions that we executed by making these pins going high and low, and doctoring the content of the indirect register and also the instruction register. So, are there any questions about what we have just done? It's no fun really being the processor. Okay, there's a lot of little chores to keep track of, and that's why that's why we need a microcode controller, because you don't want to have to do it by hand. Okay, but at this point, it's if we take a step back, okay, without paying too much attention to the individual pins, when to clock which one and whatnot, we have laid out all the major components except for the microcode controller inside the processor. There's only one thing that is external to the processor in this picture. Everything is inside the processor except for one thing. That's the memory chip. In other words, the only thing that is not a part of the processor is this component over here. That's the only thing. Okay, it is outside of the processor. Everything else that we have seen, that we are seeing here on this picture, they're all a part of a processor. Okay, and to make it relate directly to the topics that we'll be talking about for the rest of this semester, the opcode that we are dealing with, the binary code of instructions, is basically what is going to be loaded into the instruction register. In other words, at least for certain instructions, some of the bits of the instruction, of the opcode, the binary bit pattern of the instruction, is going to be used to specify, which register are we dealing with here? Which register is serving as the input? Which register is serving as the output? The other 4 bits, we're not dealing with it yet, okay, because it will tie into the microcode engine, that hopefully eventually I will put into this design. The other thing has to do with the ALU. The ALU is not having any type of glue logic yet, So it only has these 3 pins to specify what operation we are dealing with. But in the real processor, these 3 bits are, possibly more, possibly wider. It still specifies which operation are we dealing with inside the ALU, and then of all of those operations, we select one to become the output of the ALU, and then we use it to update, in this case, our register. The x86 architecture is a little bit more complex than this, so you can actually update memory content directly from the ALU. It doesn't have to go through a register. A RISC architecture, on the other hand, has very few instructions, so it has. With a RISC architecture, what it means is there's usually only one way to do something. Okay, you cannot just say, oh, these 3 instructions together can do this thing. These 4 instructions together can do the same thing, and this one single instruction can do the same thing too. That's a typical characteristic of a CISC architecture. With a RISC architecture, each instruction can only do this much, and as a result, you only have like one combination of instruction that can do a particular task. All right. So is that okay? I mean, if you're not like looking at a really, really detailed level, is the overall concept understood? Okay. The most important part here has to do with registers, the concept of indirection, and also how memory is external to this entire thing. I'll do one more item. Okay, it's called indirection, and it is really the same thing as what you understand indirection is in C and C++, which is the asterisk operator in C and C++. So we'll do just one more thing. Okay, just one more. So this time, what I'll do is I'm going to one particular location. Let's say 20 here, and in location 20. I'm going to specify, let's say, 7F here, okay? That is the location that I want to update using register A, okay? So my intention now is to first read from location 20 in memory, put that content into the indirect register, and then go to that location and update location 7F using register A. Are we doing okay so far with that concept? Let me just write it down first, so that we can track what we are planning to do. So step 1 is to read location 0 into the indirect register. Step 2, use the indirect register to update memory from register A of the register bank. Okay, so this is indirection because I'm not directly specifying which location I want to update. I leave the location that I want to update to be determined by a particular memory content, by location in memory. Okay, so it's a little bit different from before because I'm not just going to doctor and specify the content in the indirect register. I want to load the content of the indirect register itself from memory, event in the end. Are we still okay? Okay. So let's go ahead and see how we can do something like that. Okay. So if you just analyze the pathways, the output of memory can only go into the register bank. Okay, because you can see that the output here, which is the address bus, the data bus, only goes into the registers. So from the registers, on the other hand, we can update the indirect register. Nope, I take it back. The output of the data bank can directly update the register bank. So that's that's actually fairly typical of a computer architecture too. So what we can do now is to go to the program counter itself or the indirect register itself. Okay. Sorry?
That's instruction register, not indirect.
Say again?
That's the instruction register, not
Oh, that's the
indirect.
instruction register. We are talking about, okay, we should be talking about the indirect. Okay, the indirect register only has connectivity from Oh, it has connectivity from the data bus as well. So we can load directly from the address bus into the indirect register. Okay. All right, so this time we're going to use, let's say, the PC. Okay, we haven't used the program counter for a while, so now it's time to use the program counter. The reason why we use the program counter, because there's usually one single instruction to do all this stuff here, is to load indirect from a certain memory location. So we'll use the program counter for this purpose, and the location that contains the 7F is 20. So we'll go to the program counter and we'll doctor that one. So the program counter is now doctored to have a content of 20. This output goes into the input of this mux here. We'll select 1 here to basically specify, use the program counter to specify the address of which location we are dealing with. Go to the memory module, and then we want to say you are selected. We are now specifying a read operation, so don't try to override that location. We're just reading. There's no need to use a clock. At this point, the data bus is already driven. The data bus goes all the way to here, to the mux. The mux needs to select 0, so we have to turn this into a 0. So we are not using the ALU output to drive the data bus. We are using the memory chip to drive the data bus. Out of the mux here is the content of the address bus, and it goes straight into just the registers. I thought that was another path. No, I take it back. Okay, so it can only go into the registers. So into the registers, we now have to specify one particular register to store the content of what we are reading back from memory. Let's pick one that we haven't used already. Let's pick register C. Okay, register C is going to specify a 2. This will specify register C. So now register C is now specified, in bit 0 to bit 1, which is used to specify port 0. The input part of the register is now specified to be connected to register B. So we say, okay, let's go ahead and update that register, clock it. So now register C should have the content, should have the value of 7F. We just read, this is a load instruction. So the next instruction is to specify, let's use that register to specify which location we are reading from. So the next instruction is going to specify the following. It will specify, take the output of the output port 0 of the register bank should be coming from register C. So now the output of this part here, which connects to the indirect register, is the actual output from register C. Register C, you can see, has one, oops. Oh, it's not updated yet, because we have to first enable the write. We have to first assert write enable, and then we update it. Now it has 7F. Now that it has 7F, we can use the mux to select, okay, this time let us use the indirect register to specify the address line into the memory chip. And what we want to do is to use the indirect register to update memory for register A. So we have to go back and specify our registers to be 0, 0 again, because we want to use the sum of the calculation to update the memory content. So now we slide all the way to the memory here. This time we are using a write operation and clock it. And so this time we store the sum of the addition that we did earlier into a memory location. But the tricky part is the location that we store to is not hard-coded into the instruction. The 7F was never hard-coded into the indirect register nor the program counter. It was stored in memory earlier. So this is effectively doing what the asterisk operator is doing in C and C++. It is indirection. you are using a particular variable to specify a location to either read from or to store to. Are there any questions about these steps that we have just performed? Questions? Okay, because all of this stuff is related to the instructions that we'll be talking about. All the addressing modes, the instructions that we'll be talking about, it's all going to be related. Yep. The good thing is, the bad thing is it's tedious. Okay, there's a lot of details to track. The good thing is it's all recorded. Okay? I will give you a summary of all the stuff that I talked about. Like the summary of all the pins, which one should be turned on first and which one should be turned off next. But in terms of the capability of this processor, it has most of the things that we want to do in this class already. Okay, it's still lacking some of the instructions, like compare instruction. It only updates the carry flag, which is not even stored at this point. But for the most part, as far as registers and memories are concerned, we got just about everything that we need to do. So we are ready to move in to talk about the first instruction of the I386 instruction set. Okay. We are kind of running out of time today, so I'm not going to go too much into this particular node here, addressing mode and memory allocation. But we'll get started today because I just want to kind of connect all the concepts that we have talked about so far to something that is really the core part or part of the core of this particular class. Okay, so we'll talk about the move instruction. Now the move instruction is very, very general. It's very typical of a cisp architecture. Is they kind of roll many different instructions into one single mnemonic. MOV is a mnemonic. It is just an abbreviation of a word that we understand, so it makes it easier to kind of say, oh, okay, this instruction is going to copy from one location to another location. So in this case, we talked about this already. The move instruction starts with MOV, and then optionally you can specify one of these three with specification: B for byte, W for word, which is 16-bit, and L for long, which is 32-bit. And then it is followed by two operands, okay? One operand to specify where we are copying from, and one operand to specify where we are copying to. So we have the source and also the destination. Next slide. We talked about all of this stuff already. The immediate operand is preceded by a $sign. It's really just the value that we are copying from, okay? It's not a location, it's not a register. It is just the number, the bit pattern that we are copying from. The other one is a register, so you can specify one of these three as a source. You can copy from a constant and just say that, okay, these 8 bits are exactly the 8 bits that I want to copy to the destination, wherever the destination is. The other source is a register, which means I want to copy from this register to the destination. Now, the destination can be a register or can be a memory location. But in this case, a register is one of the basically 8 registers that we can select from. But it gets a little bit more complicated when we talk about the i386 processor. It has to do with its history. Okay, what is the ancestor of the x86 architecture? The 8080, and then the 8008 is the earliest one. I think the 8080 is the second generation, and then the 8085, and then the 8086. But at some point in that history, it was an 8-bit processor. Okay? So registers back in those days were, guess what? 8-bit wide. Okay? Makes sense, right? Because the ALU can only process 8-bit at a time, so it doesn't make sense to make your register any bigger than that, because you cannot really store the result of your register is wider than the ALU, so why make it so wide? Because the output of the ALU is only 8-bit wide. So as a result, the x86 or the i386 instruction set still has the ability to specify 8-bit registers. And then later on in time, with the 8086, it becomes a 16-bit, quote-unquote 16-bit processor. In other words, the internal ALU width is 16-bit wide. So at that time, it makes sense to make the registers twice as wide, right? Because you can now specify the input all 16-bit at a time, and you can store the output all 16-bit at a time. And then later on, with the i386, the internal ALU became 32-bit wide. So the registers became, guess what, 32-bit wide. Okay. But when you look at the history of all the software written for this entire line of architectures, we had 8-bit instructions, we had 16-bit instructions, and then we had 32-bit instructions. And as a result, the instruction set is kind of complex because it can look at things from different perspectives. Okay, you can look at the same thing and say, oh, we only want to look at the 8-bit portion of it, the least significant 8-bit, and make it an 8-bit register. Or sometimes I can say, oh, let's look at the least significant 16-bit and treat it as a 16-bit register. Or I can look at the entire 32-bit as a 32-bit register. Now with the 64-bit architecture, the instruction set is expanded to have the 64-bit instructions to look at a register which is now 64-bit as one single thing. So this part is probably best illustrated. We are running out of time, but I'm going to try to use a spreadsheet to kind of illustrate this part here, because this is going to be one major source of confusion is, okay, but how many registers are we talking about? Okay, so we'll only talk about a single register here. Okay, this is called register A, and by the way, the registers A, B, C, D are not just using the alphabet in a sequential order. They actually have special meaning. A actually stands for accumulator. Accumulator. Looks right? Accumulator. Looks right to me. The spell checker didn't complain. Okay, so what we want to do is to look at bit 0 to bit 7 of the 32-bit register, bit 8 to bit 15, bit 16 to 23, and the most significant part, which is bit 24 to bit 31. So this particular row, okay, I'm gonna make it a little bit better. Okay, bit positions. Okay, so these are just referring to the bit positions of the same register. It's a 32-bit register. Okay, if you want to just refer to bit 0 to bit 7, it is called the AL register. If you only want to refer to the bit 8 to bit 15, it is called the AH register. Accumulator low, accumulator high. Okay? If you want to refer to both, if you want to refer to bit 0 to bit 15 as one single thing, it is called AX. Right? If you want to look at all 32-bit, basically the entire thing, it is called EAX. Okay, we are talking about the same register. We are only limiting in terms of which part of the 32-bit register are we looking at. Now, you might notice that bit 16 to bit 31 cannot be addressed individually. Okay, you either look at these two, okay, column B and column C, as a part of EAX, or not. They do not have any specific name. There's no way to get to only these 8 bits or these 8 bits. Are we doing okay so far with this picture? Yep.
But can you address just 31 through 16 with like an AXH or something like that?
Sorry?
Could you use an AXH?
No. 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 Okay. If I highlight these things, you will see better. So I'm gonna change the background color. So let's pick a different color. Let's pick pale color here. So the color is really just we are just talking about what portion can be addressed as what name, and you can see in this case you can clearly see the cells that do not have any color cannot be addressed. So you can refer to, you can get to bit 16 to bit 31, but only as a part of EAX. Yep.
Is there a specific reason you can't access those specifically?
There's just no need, because the backward compatibility only needs to get to the earlier or the least significant bits. So the more significant bits tend not to have any particular use of, oh, we just want to address those particular bits. But when you go backwards, there's a particular need, because if you want to do any type of sign extension, it makes sense to load the least significant A bits and then expand it to become a 32-bit number. Yep. All right, so because Mr. Fox is here to chase me out on ending today's lecture at this point, I'll be over at the lab, even though we don't really have a homework assignment.